Okay, guys, so today we're going to start in on Chapter 7. And Chapter 7 is all about gases. And, I mean, well, it's not completely about gases. There's a little bit more about solids and liquids. And we're going to focus on gases and kind of what makes different phases different. So this is kind of where we're going to start. We're going to talk about, we talked way back in Chapter 1 about the different phases of matter, different states of matter. Now I'm going to talk about why, we're going to get into talking about why some substances are liquids and some are solids, and what causes something to melt from a solid to a liquid, etc., etc. So let's start talking about the kinetic molecular theory. Now the kinetic molecular theory is, it's kind of this broad idea about how matter behaves at the atomic level and what makes the different phases different. And it really comes down to this. I'm not going to, describe the kinetic molecular theory in like a super formal way. But here we go. So I'm going to start by talking about go back and kind of talk about the three phases of matter: solid, liquid, gas. And there's four common properties we use to distinguish them. One is volume and shape. So whether, and this is what we talked about back in Chapter 1, volume and shape, whether they're definite or indefinite, and the combination of volume or shape being definite or indefinite, those different combinations give us different phases of matter, different states of matter. Density, there's sort of a general density change. Compressibility. So here I'm talking about how much I can, if I put pressure on the matter, how much does its volume change? How much can I squeeze it and compress it? Thermal expansion. How much it expands, how much the volume changes when I heat it. So sort of that density change with temperature. So here is sort of a breakdown of the different states of matter. So solid has a high density, both its volume and shape are definite. We talked about that already. So it's very dense. The compressibility is small. You can't really compress matter very much. Piece of metal, you can't really squeeze it. It's already packed in pretty tightly. And kind of, if we want to look at it, because solid looks like this, right? The matter is already packed in. There's no room for it to squeeze in very well, right? And the thermal expansion is very small because there's not really anywhere for the molecules to go when they heat up. Because remember, temperature is a measure of kinetic energy, right? So it's a measure of the motion of the particles. Liquid also has a high density. Its volume is definite. Its shape is indefinite. Water can't really be compressed either, or any liquid, and its thermal expansion, it does expand, but not much. Now, don't get confused thinking about like pipes freezing and bursting. That's not what we're talking about. That is from it changing from a liquid to a solid. But when you heat up liquid, it doesn't expand very much, right? And what's going on here at the molecular level is they're connected, but they're not so rigidly attached that they can't move past one another. But they're constantly bumping into each other. They're in contact, they're just a little more loose. Finally, gases have very low density. Gases have both indefinite shape and indefinite volume, and you can compress them a lot. And they have some definite thermal expansion. If you heat up a gas, it definitely expands. I mean, if you consider putting like a aerosol can in the oven or heat up an aerosol can, it'll burst because that gas wants to expand. So here, when we look at the atoms of a gas, the particles are just loosely moving through the air, and they're not even attached to one another. They're just bouncing around. So there's lots of space. This is why it expands to fill any volume. It's very compressible. This is wise because the gas is completely detached from itself. Now if you think about it, along the continuum, if you have at one end of the spectrum solid, with its particles all smashed together, and at the other end gas, where along this continuum do you think liquid is? Do you think liquid is smack in the middle, or do you think it's closer to that of a gas or a solid? Hopefully what you're thinking is it's actually more like it's over here. So here's liquid. Its it's much closer to a solid, right? And what I mean by closer is the energy change, the energy required to melt a solid into a liquid is very small compared to the energy required to boil a liquid into a gas. It's a much bigger energy jump from a liquid to a gas than from a solid to a liquid. Okay, so now, having gotten all that out of the way, let's talk about the kinetic molecular theory. There's several tenets of it. So one of them is that, so there's 5 basic statements. I think your book, this book, oh no, it's still 5 statements. So matter is composed of tiny particles of definite size that don't change size. So this is somewhat in accordance with the atomic theory. So we're thinking of tiny particles of definite size. Now that sort of this only goes against what we've talked about in that the nature of electrons and the electron cloud means that their size isn't quite so definite as it might seem like. So in the kinetic molecular theory, now remember, any theory is just trying to explain particular aspects. And so in this theory, we're trying to explain certain behaviors. So this is a model that simplifies a lot of things. And in so doing, doesn't get everything 100% right. But matter is composed of tiny particles of definite sizes. So we're kind of thinking of them of little spheres or little marbles bouncing around, definite size. They possess kinetic energy. They are in motion. Now, what's important about kinetic energy? There's a couple points that are really important. It's equal to mv squared. So it's the mass times the velocity squared. So the mass of each particle isn't changing. And remember, kinetic energy increases with temperature, right? So it's associated with increase in temperature. So since as you increase the temperature, you're increasing the kinetic energy of the particles, and because of this, you're definitely not making them more massive. You're not changing the mass of them. What you're doing is changing their velocity. So the higher the temperature, the faster the particles are moving. And another thing that's really important to know is that at any given temperature, so if 2 different substances are at 25 degrees C, they have the same kinetic energy, right? So water at 25 degrees C and CO2 at 25 degrees C their particles have the same kinetic energy. So one is a solid or a liquid and one is a gas, and we're going to explain why. Even though, and this is going to kind of come at the end of the chapter, even though they have exactly the same kinetic energy, one of them is stuck together as a liquid and the other is a gas. So there is a reason, and we'll get to that. And really, actually, I can sort of get to the answer of that right now. The mechanics of it will come later. But the particles interact with each other through attraction and repulsion. This creates potential energy. So potential energy is stored energy. So particularly, this comes from in substances, in chemical substances, we're talking about potential energy from the attractions of particles in the substance. So the more 2 particles are attracted to one another, right, the greater the potential energy, right, more potential energy. And this is the answer to the question between water at 25 degrees C and CO2, both of them at 25 degrees C. This is a liquid, and this is a gas. And we'll kind of see more of the pieces of the puzzle here. So kinetic energy increases as temperature increases, and particles transfer energy through collision. So let me discuss those last couple tenets here, which is, so as I said, higher temperature means higher velocity of the particles. And particles transfer energy to each other through collision, so they're not losing the energy, right? One particle runs into another particle, and then it transfers some of its kinetic energy to this one. So this one ends up moving faster, this one slows down a bit. And that's basically the idea of kinetic molecular theory. That's not just explaining gases, that's this is the foundation. These are the tenets that explain solids, liquids, and gases. So again, just to kind of run through that, we have tiny particles, little spheres, bouncing around with some kinetic energy. That kinetic energy is related to the temperature. The higher the temperature, the faster they're moving, the more kinetic energy they have. That kinetic energy can be transferred to each other through collisions. And then there's a competing force of potential energy having to do with the attractions of the particles. So this idea of solid, liquid, gas, it's not just about the kinetic energy. It's about the balance between the kinetic and potential energies. It's that balance. That's what makes something a solid, a liquid, or a gas. Okay, so as far as physical states are concerned, kinetic energy, remember, and kinetic energy comes from the temperature, right? So kinetic energy is competing with potential energy. Potential energy comes entirely from the chemical makeup. So this is the part of the identity of the substance. So that's what gives us the potential energy. Kinetic energy comes from the temperature. So potential energy, which is the attractive, really when we're talking about potential energy in this context, we're specifically talking about how much the particles are attracted to each other. Again, this is part of the identity of the substance. So one substance may have, the particles in them may have greater attraction to each other than in another substance. And they tend to want to make the matter hold close together, meaning it tends on towards the solid end of the spectrum. We call this a cohesive force. Kinetic energy tends to pull the particles apart, meaning the particles want to bounce around, they want to move, they want to get away from each other. And so this tends towards gas. So the answer to the question of why, so going back to water and, so we have water and we have CO2, both at 25 degrees C. So one of them is a liquid, one of them is a gas. Now they both have the same kinetic energy. So what's happening is water is sticking together, right, in the liquid phase, where CO2 is not. CO2 is free to move around. So they have the same kinetic energy. The answer is in the potential energy. H2O has greater potential energy. Or we could say that has greater attraction between molecules. Right? So greater attraction between molecules means that the molecules stick together more. Now we can disrupt this, right? I can turn liquid into a gas. What do I have to do to turn liquid into a gas? Well, I have to get its temperature above 100 degrees C. I have to put enough energy into it to increase its kinetic energy enough to overcome this strong attractive force and disrupt them and blow it apart into a gas, right? But if I lower the temperature, right, if I have a liquid and I lower the temperature, what happens to it? It freezes because at a certain point, we lower the kinetic energy enough that it can no longer compete at all with the potential energy, and the potential energy makes it stick together more. So, there's kind of two things going on here. For any substance ever, any substance, if you have at low temperatures, you have it as a solid. I should write temperature as capital T. You have solid, and as you increase the temperature to high temperature, right, you have a gas, and somewhere in here it goes from solid to liquid to gas, right? Because we're increasing the kinetic energy. down here at solid, the potential energy overwhelms the kinetic energy. We increase the kinetic energy, it's starting to compete, it makes it act as a liquid, and then we increase the kinetic energy even more, and then it just completely separates into a gas. These points are different for each gas, or not each gas, for each substance, right? It depends on the attraction of the particles, right? Now, let's talk about what these divisions are, right? So, this division here is the melting point. This here is the boiling point, right? Right? As we increase from solid to liquid, it melts to a liquid, and then we go to a gas, it boils to a gas. Where is the freezing point? It's the same thing. The melting point and the freezing point are exactly, literally the same thing. It's a matter of direction, right? Because ice melts at, if you have ice that's below 0 degrees C, and you heat it up, at 0 degrees C, it melts to water. But if you take water and you cool it down to 0 degrees C, it freezes, right? It's just a matter of which direction you're pointing. So this is also the condensation point, right? So boiling point, condensation point are the same thing also. They're just the divisions between them. Now, if you have two substances, and one of them has greater attraction to each other, to itself, what happens to its freezing point? Hopefully you said the freezing point is higher. All the points are higher. Stronger attraction leads to greater melting point, freezing point, boiling point, whatever, right? So, greater attraction between particles means increased fill-in-the-blank point. Boiling point, freezing point, whatever. Because now we have to get the kinetic energy even higher to get it into that next phase. Does that make sense? So greater attraction is going to mean that there's a higher temperature at which something is a solid. This is why, because water has greater attraction between its particles than CO2, at room temperature, water is still a gas, or still a liquid, and CO2 is a gas, because it's still below its boiling point. So again, I'm going to draw two different things. I'm going to draw, so here's temperature increase. Now this scale is for the same, so I'm going to draw this as, this is water, and this is CO2, right? So here's room temperature. I'm going to use black is solid, blue is liquid, and red is gas. So here, blue is a liquid at room temperature, but CO2 is a gas. And every temperature above that, CO2 is a gas. At some temperature up here, though, water actually boils. Now, there's some temperature down here at which CO2 will actually condense to a liquid, right? And then we have, it will actually condense to a solid, right? So, water freezes above that. So notice that the phase transition points here, so here, here, and I didn't do a very good job with CO2. Let me fix that. Oh, no, I did a fine job. I don't know what I was thinking. Never mind. Here, here. Notice how each corresponding point is lower for CO2 because it has weaker forces, it has weaker attraction. So it's easier for it to be a gas or a liquid. It's easier for it to be a higher energy phase. Okay, probably beat that into the ground at this point. So, potential energy is based on identity of the substance, doesn't change with temperature. At high temperatures, you get liquids and gases. At low temperatures, you get solids. And I'm going to leave it at that. I'm not going to dwell on that anymore. So hopefully that makes sense.